Full house. There's a bad one I didn't notice. Right after our break, huh? Everybody's back.
Okay, we've got a Hamiltonian approach to this ancient war machine as a first topic. And this is a chance just to see once again the procedure that converts a Lagrangian to a Hamiltonian. And also see what we found when we did just the polar coordinate Hamiltonian, that the algebra is more complicated. And for a complicated problem like this one, that, as you'll see, is a kind of a roadblock. But Hamiltonians are good at doing some symmetry operations. So I'm going to talk today about what's called canonical transformations. And these are transformations, if you want, you can mix up the position with the momentum, virtually do anything as long as you keep the invariant, a Poincare invariant. You don't violate that in some way, and it's actually pretty hard to do that. And we'll talk a little bit about that as we go through this. And then what I'd like to do is go ahead and find an algebraic approach to the Trebuchet using the Hamiltonian. And indeed, the advantage is to find something that's conserved, a momentum that's conserved. In spite of the elegance that this Hamiltonian symmetry is supposed to have, this is pretty hairy stuff here, so I'm definitely doing it first before you fall asleep. And then what I'd like to do is just turn around and take a Feynman approach to this. First of all, I want to go over again how this relates to sports kinematics and throwing things out into the deep space. There's a basic idea of the slingshot that NASA has used to get almost all of our planetary astrophysics to happen. And I want to go over some stuff which I have given. This is a really simple way to look at the Trebuchet mechanics and compare it to something that's sort of the opposite. And that's what's going to happen right about here. There's a problem that I've put on all your desks that relates to that will come at the very end of the lecture. Okay, so not much to add right here, and remind you of the power of this thing in this slide. But starting from what we had already derived, and that was the quadratic form of the kinetic energy, and this is the total kinetic energy of both the little projectile and the monstrous mass that is throwing that car there. Car is a projectile, and that occurs right here. There are two parts to this gamma matrix as opposed to the G matrix. And I think you asked at the last thing what that involves. The G 1 1 1 2 1 3. I'm sorry, 2 1 1 1 2 2 1 and 2 2. That without the m is just the metric, and then you attach an m to that. Then you go looking at anything else that you have that's part of the kinetic energy. In this case, all there is this thing, and it's a simple polar coordinate mr squared. So once you've got that, that's what I call gamma. Okay, it's got two G mu nus in there, hiding, so to speak, but sort of hiding in plain sight. So anyway, once you have this, then that's a connection, a linear connection. between the velocities that we're dealing with and the momenta for the two angles. The angle of the main beam and then the angle phi of the projectile. Now what we're going to have to do is work a little bit with this angle in order to make the Hamiltonian happy, but for Lagrange it doesn't care. So you can just proceed and get equations in motion from it, and this will have some gravity effects, which we've already listed as we went through the Lagrangian equations. So now we talk about a differential of the Lagrangian, and in fact, if I multiply through here by dt, I'm talking about a derivative of the Lagrangian, a total time derivative. But here we're thinking of the fact that somebody might be actually messing with some parameter in the Lagrangian. And if that's the case, this extra term is needed. So we have a chain rule here for all of the things that can change that we're interested in. The two coordinates, their two velocities, and then finally anything else that you might be doing to mess around with this thing as it operated, as it went through its mechanical motions. So the basic total time derivative of this. And let's get all of this stuff on the same screens here, just to make it easy to see. We have enough difficulty with the complicated algebra that we're going to be playing with here. The L dot, total time derivative of that Lagrangian, is this expression right there, the velocity chain rule. What we then use are our Lagrange equations. It's very simple. Lagrange equations, the partial derivative with respect to the coordinate is the momentum dot. And that's true for theta and then for phi. And then the other one is the partial derivative of L with respect to theta dot. Well, that's just plain old momentum p theta. And then there's one for the phi angle. Okay, so Lagrange equations now go in to this, and that is a repeat of what we did with the polar coordinates, but now we've got a whole trebuchet here that's making trouble for us. So we simply look at that as a product derivative. That is the total time derivative of the product of momentum with velocity. That's an action term right there. These guys right here. So the two kinetic variables, product, well, that's a very important quantity if you're making connection with quantum mechanics. We're not doing that right now. We're just trying to get a Hamiltonian, but this is on the way to doing that. So we can rearrange this thing by taking the partial derivative of L with respect to the other side of the equation, and we have a time derivative of this minus L. That's basically taking this thing to the right-hand side, and that is what we've got going here. Now, trying to keep this thing in exactly the same order when we do this with just simple polar coordinates, but the basic idea is that this thing right here, that's our Hamiltonian. That's the Hamiltonian. That's the Poincare connection. Poincare invariant it's called. And it's really important to realize how invariant that is, because that is something that is connected to the quantum phase. And the phase, quantum phase, is kind of a mystery, but it's one of those things that really is invariant. And I like to think of it as a hidden clock that is there, and its reading is the same no matter what you're doing. If you do a relativistic transformation even, that clock still reads the same. It's something that you can't touch, literally, in terms of changing it in a controlled way. But just touch it at all and it goes crazy, so that's the reason we have dephasing of quantum systems. Anyway, back to classical mechanics. So this is a total time derivative of this thing called a Hamiltonian that's equal to the negative of the partial derivative of L with respect to t. Now the geometry that we're eventually going to show, where we make the final connection here with relativity and quantum mechanics at the end of this course, will make sense of the minus sign that's here and here and all of that. There are a lot of things that are sort of mysterious in this canonical approach to things that we need to make more solid. In any case, the continuation of this gives us the set of equations that are up on the wall there. And for this one, I might as well go ahead and make it into a, I hope I can make it into a going thing here. This is, let's see if that works. I seem to want to play. Let's go ahead and see if I can get it to fill the screen. Okay, good. All right, so going ahead here, the first thing in the lower left-hand corner of each of these screens, and I'll just do it with this one right here, is the first, I should say, the second Hamilton's equation. This is an equation that involves the partial derivative of the Hamiltonian with respect to a coordinate, theta in this case. And we can see just from looking at this thing, the partial derivative of the Hamiltonian with respect to theta, there is nothing here that has a partial derivative with respect to theta. These are all independent variables that don't respond to that coordinate. But this, that L there, minus partial derivative with respect to theta of that. And that's it. That's the basic idea. And the partial derivative of L with respect to theta, that's a Lagrange equation we already have here. So minus that, so it's minus the time derivative, full time derivative of the momentum theta. And we're going to see another one of these for the other variable. But before we go there, go ahead and take the partial derivative of the h with respect to the momentum. Okay, now that's something that we derived very early on when we talked about Hamiltonian dependence. It is a function of momentum, in this case the first momentum, the theta momentum. And doing that partial derivative of this quantity here, the h quantity, I immediately see that I have a partial derivative. This is 1 times theta dot, and then that's 0. And the idea is that the partial derivative of L with respect to the momentum is identically 0. We made a big fuss about that when we first talked about the Hamiltonian and Lagrange behavior. So you end up with just theta dot. Okay. That was our first Hamilton equation. And let's get it down here as well. Then the next one in line here is using theta dot as a independent variable, and that one is the Hamiltonian equation with respect to theta dot. That's identically 0. But if you go ahead and do the partial of this quantity, that's what you get right there. And that's just a re-expression of the Lagrangian identity for momentum. P is equal to partial L with respect to theta dot is coming up there. Okay. And let's see, the next stop would be with the PHYS. It's the same story. Cross out any dependence of h on velocity. So I end up with a first equation now of Hamilton, but now for the angle phi, the projectile angle.
in our case. Okay. So basically, what we say here is, by assumed Lagrangian functionality, we get these Hamilton's equations, and that is going to be the way it is for any of mechanical systems. This is the story right here. So this is the last time we look at a simple derivation of the Hamilton equations. Now, just for your memory purposes, these things are up here in the Hamiltonian region of this wall of formulas over here. And the third equation here is a really weird one. That the total time derivative of Hamiltonian is minus the partial of L with respect to t. L has no explicit time dependence, which we mostly do for almost all the problems that we're looking at for the next few weeks here. If that's the case, this is 0, and h is a conserved quantity, will not change with time. Okay. Let's see if there's anything else that I need to put here. This is just reiterating what we have written down here and on the wall. Okay, now, that's really nice general stuff, but we've got work to do here. I need to take the Hamiltonian definition of our Lagrangian, that is the fact that it is this minus L, the sum here over the momenta times the velocities, and write out these quantities. The idea being here that what we've got here is numerically correct. Okay, that put all these things together, and you get something that's numerically correct. That is, it's an okay equation, but it's not differentially. That is, it's not something that will be of use. Hamiltonian must be an explicit function of momentum. So we've got to convert this, and that's where it gets complicated. That's where the algebra comes in and makes the Hamiltonian procedure just for doing straight mechanics kind of a mess. So that we're going to see. We're going to go ahead and work through that. But in any case, at this point, I have here something that I can just replace the covariant metrics with the contravariant, and then be summing over the momenta that are in covariant quantities. So that beautiful duality of our mechanical variables makes it easy to remember how to do this particular switcheroo here. So this is the kinetic energy written entirely in terms of momentum, and all you need are the coefficients of this matrix. We're going to make that point lots later on. But right now, just going to go ahead and write it out as best I can in the terms of the masses and actual angles for the Trebuchet. So this is what we're dealing with for this thing. Okay, and you can see already we've got a problem in the sense that the algebra is complicated by having a denominator factor. Okay. All right. Now we're going to go ahead and see what the equations look like. At first, it doesn't turn out to be so bad. And while I'm at it here, I'm going to, in the far screen, put what we've just written down, the general equations we've just written down. So I'll let this screen jump ahead to, well, I'm getting a little far ahead here. I'm just going to stop with this particular set of algebra. And in case the coordinate equation here, I do this thing. So I go back and I look at that Hamiltonian that's written at the bottom of the far screen and take the partial derivative with respect to p theta. Not so bad. So now I've got an equation for the time derivative of theta. And the same thing with the variable phi. Okay. And these are the relations that this little quadratic form has to make it work. So the job that we always have whenever we write anything is that to get this thing formally correct, convert all your contour velocities to two covariant momenta. So remind us once again that that's part of the job that we have to do here to make this happen. So this equation then becomes this. Okay, it's already getting a little complicated here. So this is our total time derivative for the two momenta. It's roughly similar formulation, except that this one has a force associated with the launch arm, theta, then the projectile arm, phi, has got a different force on it, and that's going to be where the gravity force enters into these dynamics. And then we go ahead and just expand the thing a little bit and try to make a little bit of sense out of the thing, just writing out the quadratic form there. As I say, this is a messy factor, so I just write messy factor times sine theta with the phis on f phi there. And, well, to make a long story short, this thing really shows that you have a lessons in the inelegance at that just algebra that you're after here for writing the equations. Hamiltonian things may be very elegant formally, and I'm going to try to demonstrate a little bit of that, but I'll be shown to be a liar there too. If I say it's very elegant, it's only sort of elegant. Anyway, this is what happens just as far as the mathematics of this whole business. Okay, so what I'd like to do is show that it's actually canonical transformation. That's a transformation of not just the coordinates but also the momenta that can make some sense, make some something that works well for us. And this is a picture that is on the cover of the mechanics book that you have. What we're going to do is we're going to, instead of using coordinates that are shown in the extreme right-hand screen, fourth screen, in which all of the angles are measured relative to the laboratory, or shall I say, star fixed frame, an inertial frame. And now we're going to have a coordinate that is relative to some part of the structure. That is, I'm going to make the angle of the projectile here be based, B for base, but based on the beam, the throwing beam relative. That is relative to the normal line to the beam. That's the definition of a new angle that we're going to have. And how do you handle that when you're doing canonical mechanics like we are? We have here definitions of this. I'm going to make a theta b right here, be the phi here plus pi over 2. Okay, so, and then I'm going to have this thing be the difference between those two minus pi over 2. This is just a quick way to get into a set of angles that are based on part of the structure, the biggest part of the structure, the thing that's doing the throwing. And this is a Jacobian, a new Jacobian that we're going to have to deal with. It's not very hard to figure it out. These are all linear coefficients of 1 or minus 1, so I end up with a matrix here that represents each of these 4 derivatives. So that's our transformation. Now, remember lemma 1 back in lecture 9, which said that the Jacobian and the velocity Jacobian, that's the coordinate Jacobian, here's the velocity Jacobian, are equal. Okay, this is what we use to derive the Lagrange equation, right? So that then lets me write an equation for the velocity. And I also point out here the inverse of this thing, very simple. Okay, this Jacobian inverse transformation. Here's the transformation. Here's writing it out. It's inverse. Okay, just to check it, but that's what we have to do with it. Now, the point is, when you're mixing things, and in general, we would mix this with momentum possibly. But even here, when we're just mixing coordinates, I want to make it clear that Poincare invariance is something we really want to respect. Otherwise, you're going to be in trouble and not get the right answers. So this Poincare invariant is the mean invariant. That is, when I do this, I better get the same form for the new momenta and coordinates. So the question then is, what are the momenta doing when I made this coordinate transformation? And that's the sort of the tricky and hard part of this. But as it turns out, I'll put it on the screen too here, the transformation for the momentum is the transpose inverse of the transformations that occurred here. So in each of these cases, I take the transpose of the inverse here, that's this thing right here, and then this one, same thing for this, okay? That gives me the correct thing. And the reason I do that is to make sure that when I use these new guys here, I get the same thing. So I get this transformation, and it's inverse right there, so that I end up automatically getting the new scalar product of momentum and scale, the new action as being equal to the old one. That's something that is, really kind of hard to understand. But this is the simplest example I can give to you in a real mechanics system. Just doing this with polar coordinates doesn't look like much, but here it makes it's something worth noting. Okay. So we take this original Hamiltonian and do some stuff to it. That is, get it into the beam relative setup. So I'm going to go ahead on this screen down here and get that much. Here's the old set of equations, or old Hamiltonian, and what we're going to be writing here very shortly will be the new guy. Okay. So this is what we're after, and I'm going to make sure this one's got that. So that's the next step, is to go ahead and make a Hamiltonian that's here. And what's neat is that this one has, well, it has a dependency on phi b. That's pretty obvious. There it is. There it is. But the theta b is missing. So we've got a Hamiltonian here that's not an explicit function of one of the angles, the beam angle. That's really the important thing here. So we go ahead and rewrite this Hamiltonian. This is just a big quadratic function here involving the difference in these new momenta, and then here's the momenta squared, and that. It takes a bit of fooling around, and this is the inelegant part of this, going through and putting the right values in for the old angles in terms of these new ones to get this expression in its raw form, and then go ahead and do some more work on it. That's what we're really after right here. I'm just moving everything up on the screen here so that I have a quadratic function of momenta, I have here a linear function of momentum, and here I have this thing squared. We still have to do some work on that. So let's get all that stuff lined up here. So we're going to rewrite this so it's a quadratic equation in momentum. We're going to solve it. That's basically the idea here. And I'll do that down here. Okay, got to rearrange a lot of stuff. But that's what we're after, right there. Almost, I should say. It's a bit of rearrangement that has to happen. I'll take the quadratic guy and put it first. It's got this coefficient. So there's your A coefficient for a quadratic. There's your B coefficient for this. That's the linear. And then all the rest of this is stuff that's just function of angles. But we're making the quadratic equation for the momentum of the projectile arm. So this is an attempt to get something that will work. Now, one of the things I guess I've sort of mentioned here is this isn't going to help us a whole lot to a solution unless I consider the case of zero gravity. Now you might say, well, that's not Trebuchet business at all, but it is. It's the Chinese Trebuchet. The basic idea of the Chinese, and this is 3000 BCE that they come up with this, okay, way ahead of the West on this particular weapon. But remember what it was, all of the warriors had a rope attached to the rear end of the trebuchet, and 1, 2, 3, you get a heck of a lot of momentum put into the arm. So what we're going to do here is assume that momentum has been put into the arm and figure out what happens as a result of that to the thing that's being thrown. So this is kind of like what we first did with the Super Bowl, right? When we did the experiment, of course, we dropped it, and that's gravity bringing it to the floor, and then it exploded or did whatever it was going to do, okay? We're doing a similar thing here. We're just assuming that the forces that the trebuchet involves, and you've got a lot of warriors pulling on this thing, okay, is quite a bit larger than the effects of gravity. And that's what we do with Super Bowl. We let it get its velocity through gravity, but then only at the last minute we look at what happened to make it explode, right? And those forces were much larger than the weight. And so it was a good approximation. Okay. Well, this is kind of a medium good approximation, but good enough to fit the data that comes from the reenactment of the Siege of Kenilworth, and I'll mention that at the end. But also, what we get are results in the case of symmetry, where I make this thing as long as this. If I have that symmetry, you'll see results that mirror the results that we got 3 to 1 and 2 for, you know, a two-fold ratio, 2 to 1 ratio, or the infinite case where we got an application, velocity amplification of 3. You're going to see that come out of this mess. That's kind of cool. Okay, that's where we're headed here. In any case, we want to write this thing as that and solve for this. And the idea being that the angular momentum, this lambda of angular momentum, that's something that we're using as a variable. Okay, let's see if there's anything else I can say here that makes a little bit of sense. There's the solution, okay, for the momentum, given the variables that make this thing work. Okay, we've got several parameters here that are inertial parameters. The sum of the two rotational inertias for this arm and that arm, and then a sum divided by the inertia associated with the actual throwing arm. Okay, so those quantities show up. The J shows up here, the I shows up there, and then in the denominator, that's the problem with Hamiltonians. You've always got a denominator that's got various combinations of coordinates to make some sort of weird inertia associated with the device, the motion. All right, now at this point I would go ahead on this screen here and get up to this point where we have the quadratic equation in the new variables, and this is going a little too far. This is where we're going to simplify it a little bit, but let's see if I've got what it is I need to have here. This is the free space trebuchet. I'll just stop there. That's where we are right now, and we'll go ahead and work out an example. Okay. So this is direct approach, and it turns out to be an analogy for the Super Ball and experiment, but just with two masses, the M1 and M2. Ball and pen is what we worked with. Okay, so here are the equations that we've already used to relate the beam relative angles and momenta to the original ones that we picked in your first go-around for the analysis of this. So we're going to rewrite this total kinetic energy, and now that we've cleared the equation, solved the quadratic equation, and just look at just this part of the kinetic energy and momentum and the relations that dominate it, and write the energy in terms of this. And this is an energy that's a constant through the motion, through the throwing motion. After that initial kick has been given to the theta line, and then it's going to result in this lever gaining momentum through large angle. And that's what we need to look at here. So the constant, we're going to imagine, well, not imagine, but the way we've set it up here, this thing is not a function of the theta b angle, so this is a constant that we can use, and that's what occurred in the trebuchet as well. We had constants for a total momentum in the trebuchet, in the Super Ball thing that we're going to claim is analogous to this. It's just that everything's in angles now, and it's all happening over a continuous range of those angles. So just to make the algebra easier and to make it so that it will have that analogy, I make this thing as long as this. That is, the r and the little l are going to be equal. Okay, let me back off just to this part. That's what we're going to assume to make the thing have a little bit of symmetry. So that will let us have the r squared be outside of the combination of sums of angle momentum and the trigonometric factors here. Doesn't affect the beam any, but this is the throwing arm that we're making simple. So for r equal to L, we have that situation. And there it is spelled out up on the top there. So what we're looking for here, and this is the important thing of it, we have an equation for the energy, we have an equation for the momentum, and we're going to try to lay those against each other for this particular. Okay, so the schedule of the launch is we start with this, and this is looking at the beam as though you were riding on it. Okay, so your beam relative as well. And what's going to happen is the centrifugal force, assuming that you start this thing just a little bit off of the beam, put it right inside there, it's perfectly on, then it just sits there. But we're going to imagine that we've jerked this thing, that is given this thing some momentum, and this thing is sort of being left behind. So it's going to swing out to the 6 o'clock position. Right now it's at the 9 o'clock. It's going to swing down to 6 o'clock, and then on through to 3 o'clock. So the idea is, how fast is it going to be going when it reaches the optimum release point? That is, it has its maximum speed. That's what we're after. Okay. All right. So let's look at the 9 o'clock. Just put the algebra down for that particular case, where the beam angle is minus pi over 2, the sine is minus 1. So I end up with this here. I get a square of the sum of the two velocities at the corresponding places. And remember, these are conserved quantities, okay? So we're going to make use of that. We're just going to call 2e, that's an expression for mr squared omega squared, and then this momentum, that's mr squared angular velocity, not squared, and that is what the situation at the particular initial site there. So the momentum is in, but now it's time for the thing to respond to that momentum, and that's what's happening next year. As we move to 6 o'clock with the phi b, the beam relative angle, now from minus 90 come up to 0. By now the beam is slowing because there's angular momentum going into the mass that's attached by L to the beam, the throwing arm L. Okay, and when we put in the values for that, we get this set of equations. Now it's just mr squared times the sum of the angles at the 0 point. This is minus pi over 2 back here. This is now the velocities that are occurring as we get to the 6 o'clock position, where theta b is just passing 0. Okay, and then finally, as we move to the place where the thing is going to be let go and fly somewhere, and that's the trouble with the Trebuchet. It's really hard to aim. Okay, you got to let it go at the right place, right? And it's really going fast. So that's indeed what the builders of this reenactment found out. And they only had so many of these concrete spheres, and they usually kind of tore them up by throwing them at 240 miles an hour. So the project almost didn't work. They finally knocked down the castle. The castle was already knocked down, but they did a wall that was integral. All right, so this is where we are at 3 o'clock. Okay, now we got to put all this together to make a story here, and that happens next year. The basic idea for this is that you look at the kinetic energy that we have here. We've got these 3 cases, and that lets us make some statements about what the energy and the angular momentum is. And in addition to that, a little another equation that comes from this, the relationship of that original omega plus the beam velocity at the pi over 2 position, which is where we are right now, and that is going to let us do some algebra here. So what we can do is write the omega here now using these two. You get this relationship of the beam angle velocity. That's what we're interested in that one. But this one, this phi dot, we have that also moving. So that comes out to have the extra 2 omega attached to it. And that lets us substitute into this thing to get a difference between the angular velocity that we've given to this thing originally and wherever it is right now at the pi/2 point, the optimum release point. So let's get that up there. And while we're at it, we can move a few terms around here and get the other relations that make this thing really work. So these are the sort of final results here. We have a final velocity of the throwing beam at this point, the green point. Okay, and here are things that just involve the masses, little mass, projectile, big mass, driver, okay, would-be driver if the gravity was still working. It's just now sitting, it's just doing what it does for the inertia. And the R, big R of the driving thing, that's a small distance. It's this distance right here. And then the little r, which is this distance equal to that distance that we have in this symmetric Trebuchet. Okay, so large M is the first thing to look at. What does this look like? Where the big mass is huge compared to the thing we're throwing. Okay, so this is equivalent to the super ball and a little tiny ball. Okay, very big ratio between the big eye and the thing being thrown. Okay, result 3 omega, 3 times the angular velocity that was given by the soldiers. Okay, just like it was on the Super Bowl. All right, that caught my eye immediately. So what do we get here? The phi dot at pi/2. Essentially equal to the original, whatever you gave it, it's still there. That's what you'd expect. You've got this thing so much larger than the thing it's throwing. Okay. Now the other possibility, and that's the one that's over on the left-hand side of the graph that we did for the Super Bowl, this one, here I'm taking an optimum case. I'm taking it so that the mr squared, that's the denominator here, is exactly equal to this, so that I get this thing, that is 1 minus 1 over 1 plus 1, I get a theta dot of 0 for the big beam at this point. Now what does that mean? That means that this beam, which started out over here with tremendous velocities, is losing it. It's losing it to the now appreciable projectile mass, and I'm saying it's just the right amount to come out with 0 as its angular velocity. Okay, so when it releases, it's not going anywhere, and it's given all the energy it had to that little guy, the little projectile. That's the optimum throw, and that's what the Trebuchet reenactors were aiming for. They just did it experimentally. You don't see them doing all of this, but they did it, you know, seat of the pants, right? And that's where they got 240 throw. And then it was just a matter of setting the angles to start the thing up. So that's the thing that I wanted to say. This is analogous to the Super Bowl experiment, remember? This is optimal throw, 100% energy transfer, okay, final velocity, 2 times initial velocity, just like the thing that we're getting here, and this ratio that did that is in a sense analogous to picking the 3-to-1 ratio for the suit. 1, 2, 3 to 1 for that throw. As compared to this one, 0% energy transfer. Fastest throw, though, you really get lots of velocity for that tiny little thing. Okay, but the big thing is not losing any compared to the little thing. The energy of the big thing is the same after we're done. Okay, now before we go any further with this, and by further I mean we're going to do a really simple way to look at just the simplification that is in the problem that I've assigned for next week that involves a comparison of a trebuchet and a anti-trebuchet. Just as sort of a flight of logic here, that's what I'm talking about. Before we do that, I thought you might like to see some more complicated things that are like the trebuchet. And this is a link that I actually filmed at NCAR. I went to visit in Boulder one time, decided in Boulder for a year, and I've never gone up to the National Center for Atmospheric Research, which is up on the hill sort of overlooking the town. A weird sort of IMP architecture for the center. It's very, very, it's been used in science fiction films as it's so weird. Okay, so up we went, and here was this thing, and I hope I can get it to work here. You can look at the thing on your own time. Here we go. Anyway, with my cell phone, I filmed this thing. Now, this isn't a trebuchet. It'll slow down in a minute, and you'll see what it is. It's basically a T with pendulums on each of the three ends. See it slowing down there a little bit? Now, in the beginning of the film, it was my hand going in there and turning the knob so that it had some speed. Anyway, this is the kind of motion that you're going to get with a 3 or 4 or 5 armed trebuchet. And there are a whole bunch of things on the web where people build things like this. The next one is something that looks like a clock that somebody made. But this one is really cool because the bearings are really super good. This is, I think NCAR probably spent several $1,000s to make this thing. But anyway, the crazy motion that you get, and you ought to watch the other one, you can see there's a point there where it really does some amazing things. So that's just something to start here. I'll just put it again. Really start it. There's my hand turning a thing, and then I quickly turn the cell phone on. But there are moments when this thing sort of slows down, and one of them has a tremendous amount of energy. And that effect is what I'm interested in for the next stuff. Is how do you get a lot of energy into a lever, a baseball bat, a golf club, a tennis racket, a lacrosse stick, you name it. How do you do that? What's going on there? And the idea is to explore the crazy chaotic motion of these things. These things are all usually chaotic. That is, they cover their coordinate space in seemingly random things. And they also eat up your precision. If you have 5-figure precision to set the initial conditions for this thing, and you look at what you have compared to something that was, say, 12-figure precision, very quickly you see the 5 degrading to 4, to 3, to 1. In other words, it isn't very long before it really is random, even though the equations are absolutely deterministic. That's what they call deterministic chaos. And it's, you know, sort of a wake-up call for all of us Newtonian, thinking we have the world, you know, to be able to predict things with mechanics. And you can up to a point, but for things like this, very quickly, it's random. So you're going at 24 figures, right? Well, it just takes twice as long before it's eaten all of that. It eats it exponentially. That's the characteristic of a chaotic system. Okay. So it basically says, calculate as much as you want, but you're dead in the end. It's wrong. Now, it doesn't mean that it's qualitatively wrong. It'll be doing weird things. Well, there's somebody that's got another one of these things. And there, it does that little loopy thing, right? Every once in a while, it just throws that thing into several resolutions, very fast revolutions. Okay. So anyway, I say the web is full of, in this neighborhood, things like this. And I've left a couple of links, and TC has some more, and maybe we'll attach those as well. Okay. So let me go ahead on this screen. And you've already seen this little scenario, so I won't make any point of that. The Montezuma's revenge, that occurred at a certain point in history. Maybe. We're not sure that that's actually what happened, but it is in one of the people's log of the thing. This is what I want to talk about. And we started the discussion of the Trebuchet by mentioning this. And here are a few more things that I could get rid of this without using up CPU time, I will do so. Let me just kill this particular set of things. This is the great thing I was showing to somebody who came visiting last Friday, and you'll be getting lots of that later on. So let me go back here to the lecture, go forward through the chaos and the Montezuma's revenge to this. This is, I think, really important because it's talking about human beings doing things, right? Building a culture. As, you know, we had to do all this stuff, and then we can't stop doing that, right? I mean, we love our sports, okay? And as I say, the psychologists have measured how addictive various things like gardening is, and it's a good thing, okay? And you get some exercise in doing all of these things. And the idea is to not have to go to the orthopedic surgeon's room after you've done too much of these things. And of course, for the ancients, there weren't any orthopedic surgeons. If you did it wrong, you were hurt, and you were out of business. Okay? And this goes to, if anybody visited this little place just outside of St. Louis, just to the east of St. Louis, one person, anybody else? You should. This is part of American culture, okay? The Indians had basically a big Walmart center at Cahokia. It's now called Cahokia. All of the trading that was going on, some of it extending all the way to the eastern and western seaboards, centered for about 200 years around the 12th century at that junction of the Missouri River and the Mississippi. But they're on the other side. They're on the eastern side, so they're out of the floodplain. And they built funny kinds of pyramids, very different kinds of pyramids that we see in Mexico. They did it all by building dirt. They didn't have the rocks and things that the Incas and Aztecs had. Anyway, it's worth seeing. And they also had this little thing. They had discovered that if you put a little lever on, I think this is another trebuchet. This is just extending so you can throw an arrow really fast. Okay, it's more trebuchet motion. Okay, and then as I mentioned, if you go to the fair, right, ring the bell. How do you get that hammer to get the most kinetic energy in? Okay, well, we'll try to explain that qualitatively as well as the quantitative stuff that we've done. If you're water skiing, okay, it's fun to take just the right path so that you snap the water skier at about 100 miles an hour sometimes. Dangerous, but still fun, right? Okay, or you're towing people on a little inner tube type thing. You go out people like this people doing that. That's another one of the snap the whip. And the 3, 4, 5 degree of freedom trebuchet motion. This is quite a few individual pieces. In other words, the bullwhip, which starts thick and gets thin, is making a wave that remains localized all the way to the end, at which point the speed goes supersonic. So what I thought was, how would it take, what would it take to make it 3-arm, 4-arm, or whatever trebuchet, and what geometry would I put it at so that when I let it go, it snapped. It is the last thing exceeded the speed of sound. That's, I think, possible. I mean, it's one of those things that we have not gotten around to doing. We need some people that are working in engineering as well as physics. Anyway, as I say, all of the analogies are to be taken seriously. The basic idea of the trebuchet, qualitatively speaking, is that here at the beginning you have a large force that's nearly parallel. That is, the force is just along that arm, particularly if it's a rope. It has no ability to put any torque on this thing in this direction, but it does have a lot of force in this direction because it's accelerating due to either gravity or the Chinese troops that are giving it a big impulse. So the velocity dot force is high. That's the amount of energy that's going into this thing. So this thing gains very quickly. Right away it's up to, well, finally 240 miles an hour, but I'm just imagining our trebuchet is not tuned very carefully at all. This is just a generic trebuchet that is the first animation on these sites that we have for this type of mechanics. And the deal here is that if you're doing golf or tennis, the real thing, besides getting the racket back so that you can point at the ball and then putting energy in a funny kind of way, that is, you actually imagine pulling the tennis racket as though the sleeve is going to come off. Try to bring the sleeve off the thing, and that's equivalent to the thing that will get a lot of energy in it, and then let it float, and at that point you can aim it. You see, you can get it so that it's just on target for whatever it is you're trying to hit. And this is particularly a problem with golf, where you have a thing back here and you imagine pulling the sleeve off of the golf club to get it going. And if you're fair, that's the thing to think about, is if you had a sleeve here, pull it off, try to pull it off. And that means get a lot of force at the beginning, and then it'll stay with you until you hit something. Okay, so that, I think, is an important thing. Anyway, to emphasize that, I have the anti-trebuchet here. The anti-trebuchet is just a tube or a pull stick, and this is something my sons discovered early on, is that if you take an old skateboard wheel, and they broke their skateboard so many times that there were quite a few wheels lying around, and a pull cue, turns out the average skateboard wheel fits pretty well over the thin part of the pull cue and stops about halfway. Okay, so you just sort of stick it there gently, and then you throw that skateboard wheel impressive distances with just this. But this is the opposite of the trebuchet, because what this one has to do is at the very last minute before it leaves the end of the lever, that's when it's gaining its velocity. It's kind of like people take exams around here, you know, you wait till the last minute, right, study like hell, right, and not get quite as good a result as if you had prepared early, as we do with the trebuchet. Okay? So the idea is to compare a trebuchet-like experiment where you cut the pull cue in half, put a hook in it so the thing can swing, okay, and then you throw that, okay, and then trouble is, this takes practice. This, you do the right the first time. This is simple. This is more difficult. And that's true of all the lever sports. If you try to force things at the last minute, you're not aiming well and you're not getting much energy. So that's the purpose of this sort of picture here. Now let's go ahead and see what the trebuchet has to offer. Well, what the and I've got to see if I've got the flinger. It's ready to go, I think, on this screen right here. Let's just see if I can get that to work, just to give you some idea. It's got the same weight mass ratios and everything, and not much of a throw. Okay? The idea is that if you can do it, if you can train yourself, this is much better. Now, we got to prove that quantitatively, and that's what the rest of this lecture is about, is doing that. But that, I think, pretty well thing. Let's just reset this thing and throw it again. Okay, so let's go ahead and pause that, and I will go back to the lecture and go forward with this. Okay, here's the basic algebra of what's going on here. And the Trebuchet, pseudo-Trebuchet, is sitting here, and both of these are like the Chinese thing that we were talking about, given a constant angular momentum. The difference here is we just keep the angular momentum the same. So there's an electric motor making the thing go at omega, that's constant. And this one too. Okay, so which one does a better job of getting speed into a mass that's sitting for a particular L? Now we're being quantitative and actually trying different ratios with basically simple energetics here. The idea is that this thing's going around and there's a centrifugal force and a centrifugal potential acting on this thing. The centrifugal force, omega squared r, and then the integral of that, omega squared r squared over, over 2. Okay, so that's the effective potential that's there. So this one, if I were to imagine going all the way to the center here with the mass, it would just hardly get going before you turn the thing completely around and miss the throw. But we're starting it already out here where it has a appreciable centrifugal force, which increases with lever arm. In other words, you end up with a potential that's like a harmonic oscillator, but it's upside down. It's minus 1/2 m omega squared r squared. Okay, so this is going to be starting out slowly, 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 but now it's starting to gain, and then down here it really picks up, but then you come to the end of the lever, whatever you've got here is what we're going to record. Whereas the Trebuchet, okay, particularly if you started back here at the 9 o'clock position, okay, if you started back here at the 9 o'clock position, somehow this is missing, but this is the 6 o'clock, and then there's the 3 o'clock position that we talked about when we were doing all the fancy stuff with the Hamiltonian. I'm going to go ahead and start it here, but we'll try it at you know, as we approach this. This is obviously getting more speed. And this is the game that you see the professional tennis players playing, is that if they're in a hurry, they'll just start at 6 o'clock and they'll get pretty much energy off that. But if they really want to whack the thing and they have a pretty good lead on it and they think they can get it off the side enough so the guy can't pick it up, they'll come around at 9 o'clock. Okay, so they're putting the energy in a lot more. They've got a whole region up to here that they've got energy, and then they keep going, right? That's how you get 140 mile an hour drive. Okay, or same thing with serve. Okay, so in golf, wow, you get a lot more energy than that from a big long club. But where you start is important. But the question is, let's just start with about the same radius as the flinger. So it's flinger versus Trebuchet here, and that's what your problem is. Okay, and I'll just go through it real quickly here because you'll see what it is you have to do to get these results. I'm asking you also to get the trajectory for some of these things. But this is the second problem for next Wednesday. Okay, so that is what we're after here. Now, you see the results here. We have the final 3 o'clock minus the initial. That's just figuring out what's the difference in energy. Where are you going to be when you started? Where are you going to be when you fall off the end? On this one, where are you going to be when you start at this particular clock, that is 6 o'clock, and where are you, how fast are you going when you get to 3 o'clock? And it's just gotten by looking at the potential energy, the dynamic potential associated with a centrifugal force. Okay, so that's going to give us some answers that we could do without very much work at all. This is, you know, sort of high school level of physics at this point. Okay? Now, there is an important point here, and that is that when this one lets go, and it's, you know, up here someplace, we're looking at all of this relative to the beam, or we're in the beam frame all the time with this thing. When this thing lets go, it's got itself a velocity relative to the beam that's outward, whereas this one has something that's relative to the beam at 90 degrees. So this one's going to have an advantage just from the geometry. That alone makes this one more powerful. But this one also has the advantage of giving you energy initially, getting it in there early, which for a free lever like a baseball bat, golf club, or tennis racket is really a key to making a better game out of it. Okay, so going ahead and working those out gives you a couple of formulas for the final velocity. When you're half-cocked like this one at 6 o'clock, or fully, and that means you would be just a little off of 9 o'clock, so the centrifugal force could act and swing this lever around. And we're trying here different lever lengths. That is for a RB ratio of 2 to 1. This is twice that, would be about there. That's this first one right here, RB. Let's see if that's 2. And L is 1, so I have 1 unit here and I have 2 units there. If I shorten this one to 1.5 and make L 1.5, that's the Trebuchet that we were talking about, equal throwing beam and, equal holding beam and throwing beam. That's this one. And then here we are doing the same sort of situation, ratios the same in each case. This is 1 and 2 versus 2 and to 1. Here they're equal, okay? You can see that this guy is way ahead of this guy. This guy's about 4, this guy's 6, okay? And as you, let's see if I got this right here, half-cocked, it's 5, fully 9 o'clock cocked, it's 6. This one we don't get to choose that, so we just pick the number that you get from going out this 2, static, the pool stick thing. So here you get a pretty good picture of what the thing is that's happening just from simple algebra. And I wanted you. Now I'm going to ask you to actually make trajectory to figure out the time trajectory and all of that of these things. But I think you see what it is we've got here. Now we're just about at the end here. I'm going to point out that there's a little bit to be said about physics when it comes to playing with these things. As I say, physics used to be pretty much bipolar. By that I mean that there were two groups that worked in physics, and they sometimes didn't talk to each other and weren't always very friendly with each other. But theory and experiment was all there was. Okay. Well, experiment's gotten more sophisticated. I don't know if theory has, but probably, because it's really a three-pointed thing. We've got all of our formulas still to talk about this covariant or contravariant Riemann equation, but we've certainly talked about all of these things so far. We've talked about the Anglo-Irish part with Hamilton and Hamilton-Jacobi, and that's also Poincaré. So it's French and Anglo-Irish. That can't be a combination like that, maybe. German approach, which we're going to get to next time. And of course there's Lagrange, the French approach. All right. U.S. approach, quick and dirty, F equal ma is kind of what we're doing just a few minutes ago. Anyway, that's theory. That's this stuff. And I'm a theorist, so I stuck it at the top, but probably ought to turn this whole thing over and put it at the bottom. And then you have the two kinds of experiment that really have to talk to each other. You take data with computers, you're going to analyze data with computers. So this is the postmodern scientific method right here that we're dealing with, and it's worthwhile thinking about that. And then questioning whether we can get a supersonic trebuchet. Okay. Anybody interested? Yeah, I can see a lot of enthusiasm for the supersonic trebuchet. Yeah. If nothing else, it would be a fairly dangerous thing. Yeah, that's why I'm reluctant to take it on. But anyway, the idea is still there, and of course, there are quantum mechanical versions of this kind of motion, and they are, I think, important too. Okay, the rest of this is just really simple. Going ahead and making a trebuchet just out of two beams, not too different from the real one, but my fixed point here, and writing equations, sort of like what we did. Now this, I was going to set this as a problem and then let you work out the optimization and all of that. That's for another time. I just throw this out as a very quick way to get the mechanics of the trebuchet in terms of the beam relative angle. And the beam relative angle is pretty obvious here. It's this thing right here. You're just measuring your angle off of the end of the beam as opposed to off of the perpendicular, but it makes the algebra a little simpler. Okay, we'll see you then on Monday, and we'll be taking the German approach to mechanics. So that will be when we do the covariant, contravariant really seriously.